Hello and welcome to another tutorial. In this tutorial, I'm going to discuss the very interesting topic of numerical integration, which has also some links to geometry, and we will explore all the different methods for doing numerical integration of real functions. Now, the main type of integration that we're going to look at is Riemann integration, and it's basically the algebraic summation of area under the function. And when we say area, we mean that the area that is basically an algebraic area, which could be either positive or negative. For example, if you look at this function, and we are integrating from a to b, so our integration interval or integral interval is let's change it to integration interval. Our integration interval is from a to b, and in this interval the function is actually crossing the x-axis, so some of one part of the function is below the x-axis and the other part is above it. So when we say the integral of f of x from a to b, we basically calculate the area under the function between the function and the horizontal axis, and whatever that is below the horizontal axis we call it a negative area. Whatever that is above the horizontal axis we call it a positive area. And the definition of integral is the summation of all these signed areas or the algebraic area. So here is a2 because it's positive, and minus a1 because this one is negative. All right, now the definition of Riemann sum, or the definition of integral based on the Riemann sum, is that if f of x is integrable with is Riemann integrable, so if it has a Riemann summation, then the integral is defined as the limit of n goes to infinity, a summation of f of x, f the function at some xi, some point in one small interval, times delta xi. This is the length of the interval I. So if this series, right, has a limit, or basically if this series converges, we say that f of x is Riemann integrable. All right, there are other definitions of integrability, but here we're just looking at the Riemann integrability. All right, and the right hand side of this summation, basically this definition is a summation, and what it means is that we basically divide the interval into very small subintervals, and in subinterval I, subinterval number I, the length of the subinterval is delta xi, and we choose a point xi in that subinterval and then evaluate the function f in that subinterval. Okay, this is the base definition, but we can have other definitions for Riemann integration or Riemann summation as well, but this is the fundamental definition that defines the integral as a series, right? If we have a summation with infinite number of terms, it becomes a series, and the question is whether or not the series converges. And if it converges, we say that the f of x is integrable based on Riemann definition, right? So the convergence of the series. And as we discussed previously in the topic of sequences and series, the convergence of the series requires that the generating sequence, this fxi delta xi, must have a limit of 0. So the limit of fxm delta xm when m goes to infinity, when we have infinite number of very small intervals, should be 0. But the function is not equivalently 0, is not always 0. So delta xm, so the length of the intervals should go to 0, right? When we have a lot of intervals, infinite number of intervals, which makes sense, right? So this delta x is basically the length of each very small subinterval. Now the question is, how do we find the area under a given function, or how do we find the integral? And the answer is, okay, we should form this Riemann summation or Riemann series. Okay, now there are different methods to do this kind of summation. One is the rectangle estimation or rectangle method, and this pertains to mostly, just for convenience, most of the time it pertains to a uniform partitioning of the interval. So our integral interval or integration interval is from A to B, and this blue curve is our function. In terms of the forward approximation at each subinterval, first of all, it's a uniform partitioning, so the lengths of all the subintervals are the same, and if we have n subintervals, the length of each subinterval is b minus a divided by n, okay? And then the forward approximation is that at each subinterval, choose the value of the function at the starting point of subinterval, all right? So the area under the curve of f of x in each subinterval is approximated by the area of this rectangle with a leading edge right at the beginning of the function, right, for the subinterval. So the area is approximated by f of xi. Xi is the beginning, xi plus 1 is the end of the interval I, times delta x, okay? And delta x is just the length of the subinterval. Now if we do backward approximation and then at each subinterval we approximate the function with a constant number, which is equal to the value of the function at the end of the interval, all right? And here it happens that this backward approximation actually overestimates the area under the curve, but it may not be always the case, all right? So in this case, we pick the value of f at the end of the subinterval I and multiplied by delta x. That gives us the area of this rectangle, all right? And then we take the infinite sum, or take the sum of n subintervals, and then let n go to infinity, all right? Now the other one is center or midpoint approximation, which means that again we have uniform partitioning, and in each subinterval we pick the value of the function right at the midpoint of the interval. So the midpoint of the interval is xi plus 1 over 2. So we evaluate the function at this point, right in the middle of the interval, and multiply by delta x. It gives us the area of this rectangle, all right? Now if we do this, any of these forward, backward, and center using uniform partitioning, when n goes to infinity, when we have infinite number of subintervals, all of these three ways should converge to the same number, which we define it as the integral of the function. In fact, there is a more general lemma or theorem that says that Riemann summation will converge to the same result, all right? So the same result is the key here for any arbitrary partitioning. So it doesn't matter if we do uniform partitioning or if like one interval is much smaller than the other one, it doesn't matter. It also doesn't matter what value for the function we choose in each subinterval. It could be the leading edge, the first value, the end value, or the center value. Doesn't matter. It always, if the function is integrable or Riemann integrable, the value of the series should always converge to the same number for any arbitrary partitioning, any arbitrary value for the function, or for any point inside the subinterval, okay? Now obviously this rectangle estimation or rectangle method quickly or very obviously gives us the fact that if we are integrating a constant number or a constant function, c, so f of x here is c, all right? So the constant function is just a horizontal line. So in each subinterval, the area of the rectangle is exactly the same as the area of the function, right, underneath the function with the horizontal axis. And then when we sum them up, we just get the value of the function times the length of the interval, b minus a, all right? So this is just comes out very obviously. We don't need to actually prove it. It just comes out of the definition of this rectangle approximation. Now in terms of calculating this Riemann summation, we typically end up with some series or sequences, the sum of some sequences. And there's a fundamental property which is the difference summation. So if we have a difference summation of the sequence, which means if we sum a sequence an, ak, and take the summation of the difference of the two consecutive terms, so ak plus 1 minus ak, from some index m to some index n. So be careful. So here the difference means there is only one unit difference between the indices of these two terms, ak plus 1. It has to be k plus 1 and k, okay? I mean, it also could be ak and ak minus 1, but what I'm saying here is that the difference should be exactly equal to 1. So this difference property says that if you sum the difference of the two terms of a sequence, the result is basically you take the last index of the sum, put it in the ak plus 1, it gives you an plus 1, minus you take the first index, put it in the am, all right? And it's very easy to basically prove. You just write all these terms, am plus 1 minus am plus 2 minus am plus 1, etc. And all the terms cancel, only the first term ak, am, and the last term an plus 1 remain, okay? That's why this summation of the difference of the sequence is the a at the last term, an plus 1 minus am, first term, all right? Now there are some useful sequence sums. So if I take the sum from index m to n of a constant number, which could be 1, because if I calculate for 1 and then for c is just c times multiply the 1, right? It's c times the number of terms in this sequence, because we're just summing up some constant number some number of times, right? And the number of times is n minus m plus 1. And what matters here is because in the Riemann sum, eventually n goes to infinity. We have infinite numbers. So what matters is just the order of the sequence, which is n, right? If you have n terms, the order is n. If you sum from 1 to n of k, so we're summing 1 plus 2 plus 3 all the way to n. And we also could include 0. It doesn't matter. It doesn't change the result. The result is last term, which is n, times last term plus 1, which is n plus 1, divided by 2. So n here represents the last term. So if the index was from 1 to n minus 1, we should have n minus 1 times n, because n minus 1 is the last term, all right? So last term times last term plus 1 divided by 2. And when n goes to infinity, the order of this summation is n squared over 2, all right? So sum of k squared from 1 to n. So basically we are summing 1 squared plus 2 squared plus 3 squared, etc. is equal to the last term times last term plus 1 times twice the last term plus 1. So n times n plus 1 times 2n plus 1, all right? N is the last index basically. So n, last index, n plus 1, 2n plus 1 divided by 6. And when n goes to infinity, n is much greater than 1, 2n is much greater than 1. So the order is 2n squared over 6, which is, no, the order is n times 2n over 6, which is 2n cubed over 6 or n cubed over 3, all right? And similarly for summing 1 to n of k cubed, which is 1 cubed plus 2 cubed plus 3 cubed, etc., is last index plus 1 divided by 2, all of it squared, all right? And when n goes to infinity, we have n squared over 2 squared, which is n to the 4th power divided by 4. This is the order of this summation, which is the most important thing to know when we are trying to calculate the Riemann series of the integral, all right? Now, how do we actually calculate these, right? How do we find these results for k squared, k cubed, or even 1 or a constant number? What we do is we use the difference property here. And if I'm trying to find k from 1 to n or 0 to n of k to the some power p, which p is an integer, in this difference property, I set the ak or the sequence to k to the p plus 1. So I increase the power of the k by 1 unit, k to the p plus 1. So if I'm trying to find the summation from m to n of 1, So p is 0. Then here I put ak equals k. And when I calculate from m to n of k plus 1 minus k, and on the left side I have 1, so sum of 1, which is I'm looking for, and it automatically gives me the result, which is n plus 1 minus m. So n minus m plus 1, alright? So that's how we calculate the sum of 1 or a constant c. If I want to calculate the sum of k, here I put k squared. So k plus 1 squared minus k squared gives me 2k plus 1. So the sum of 2k plus 1 is 2 times sum of k plus sum of 1. And we already calculated sum of 1. So it's not only this part and using the difference, but we have to also use the recursion. So in order to calculate the sum of k, first we need to calculate sum of 1. And similarly, if I want to calculate sum of k squared, I put k cubed here, and then I have some terms which is sum of k and sum of 1. So in order to calculate sum of k squared, first I need to calculate sum of k and sum of 1. And similarly, if I want to calculate sum of k cubed, here I put k to the 4th power. And then in order to find it, I need to already know the results of k squared, sum of k, and sum of 1, which I already have it. So we use this method, this technique of difference summation and the recursion that helps us backtrack the results and find k cubed by knowing the result of k squared, k, and 1. Alright? Now, how do we use this? Let's look at an example. So let's look at the integral of a linear function, just f of x equals x, over the interval from a to b. And we're going to use the forward approximation. So area of each rectangle under the curve is f of xi, which xi is the leading edge. So the beginning of each subinterval times delta x. And it's a uniform partitioning, so delta x is just the length of interval b minus a divided by n. Alright? So the Riemann definition is that integral of a to b f of x dx equals to limit of n goes to infinity of this sum, I from 0 to n minus 1 f of xi delta x. Now I prefer to use the index from 0 to n minus 1 to say that I have n intervals. Some people prefer to use from 1 to n. It doesn't matter, because when n goes to infinity, only the order of the function matters. Any term that doesn't have n doesn't really matter, alright? In terms of the fact that only orders of magnitude matters when we try to simplify the result. So if I want to find this summation, first I need to find xi, which is a, the beginning of the interval, plus I times delta. So x0 is a, right, for the first interval. x1 here is the second, is a plus delta. x2 is a plus 2 delta, etc. Which we can explicitly write it as a plus b minus a over n times I, alright? Remember, I is the variable, I is changing. So sum of 0 to n minus 1 of f of xi delta x is, we just replace f of xi by the definition of f of x, which is x. So f of xi is equal to xi, so is equal to this, and multiplied by delta x. So is a times delta b minus a over n plus I times delta squared b minus a squared over n squared times I. Alright? Now remember, I is the variable, so this whole first term a b minus a over n is like a constant, and when we sum from 0 to n minus 1 we have n terms, so we just multiply the whole thing by n, and the n cancels out. The first term, the summation of the first term gives us a times b minus a, alright, plus b minus a squared over n squared is a constant. It comes out of the summation, and we have to sum from 0 to n minus 1 over I. And remember the rule, the summation is last index n minus 1 times last index plus 1, which is n, divided by 2. And the n cancels out. We have a b minus a plus b minus a squared over 2 times n minus 1 over n, which is 1 minus 1 over n. So we end up with a constant term ab minus a plus b minus a squared over 2 plus a term that depends on n, which is our error term, b minus a squared over 2 times 1 over n, which we can also write it in this way, b minus a over 2 times delta, because delta is b minus a over n. All right. Now the thing is that when we take the limit, when n goes to infinity, this error goes to 0, obviously, which means that the series actually converges. So the integral, the Riemann integral is available, or the f of x is integrable or Riemann integrable, all right, because the error goes to 0. So the series converges. And we end up with this a b minus a plus b minus a squared over 2. If you simplify it, it becomes b squared minus a squared over 2. And the way we define this result, or the way we interpret this result, is that the integral of a to b of x dx is x squared over 2 calculated from the difference from a to b. So if the integral symbol is more like a sum, this vertical line is more like a difference. So the integral mimics a sum notation, S notation or sum. This vertical line mimics a difference notation. When we say x squared over 2 from a to b, it means take the difference of this function from a and b. So b squared over 2 minus x squared over 2. Now this function x squared over 2 has actually a name, which is called the antiderivative, and it's related to the fundamental lemma of calculus, which says that if I find a function that when I take its derivative it gives me f of x, then the integral of f of x becomes the difference of that function over the interval that I'm integrating over. So I know that the derivative of x squared over 2 is x. So the integral of x from a to b is x squared over 2 from a to b. All right. Now, just by the definition of this Riemann summation, we can easily prove two properties. One is the linearity property, which means if we integrate f plus some coefficient, some number g of x, it's equal to integral of f of x plus lambda, the coefficient, times integral of g of x. This is because this is the property of the summation, right? Sum of f plus lambda g is equal to sum of f plus lambda sum of g. And when we take the limit, it becomes integral. The other one is the breakpoint, and that means from a to b of f of x dx, we can pick any intermediate number c and break the interval of a and b to a to c and c and b. And the integral is equal to integral of from a to c and plus from c to b. Now in general, c doesn't have to be some point inside the a and b interval. It could be outside. It doesn't matter. This equality always holds. And you can easily prove the case when the c is inside the interval just by looking at this summation, because then you just have to break the index. Instead of having 0 to n minus 1, you have 0 to some m index, and from index m to n minus 1. And it gives you the summation here, all right? So this was one example that we were able to find the antiderivative of the x, which is x squared over 2. Now similarly, we can use the rectangle approximation and uniform partitioning to, for example, find the integral of x squared. Again, the same thing, xi is a plus I delta x. And then when I do the summation of f of xi delta x from 0 to n minus 1, so delta is fixed, comes out, times f of xi, which is xi squared, which is a plus I delta squared, which is a squared delta squared I squared 2 delta ai. Now here I'm not going to exactly calculate this because I already know that I'm going to take the limit of n when n goes to infinity. So I just look at the orders of each term. A squared is a constant, so when I sum it, it gives me a term n, so it's order n, all right? And delta is order 1 over n. So when these two terms multiply, it just gives me a constant number, which is a squared, times delta has a b minus a, right? So a squared b minus a. And then the second term is delta times delta squared, which is delta cubed, which is b minus a over n cubed. So it has a 1 over n cubed term. And then the summation of I squared gives me an order of n cubed over 3, right? The exact summation is this. But I don't care about the exact summation. I just want the order of magnitude, which is n cubed over 3. And delta cubed has a 1 over n cubed, so they perfectly cancel out. It gives me a b minus a cubed over 1 over 3, all right? B minus a cubed over 3. The last term is 2 delta squared times a times I, right? And the summation of the I gives me n squared over 2 as the order of magnitude. And also have a delta squared, which is 1 over n squared, proportional to 1 over n squared. So they also cancel out. This gives me a times b minus a squared. Now if you simplify this, it gives you b squared minus a b cubed. So if you simplify this, it gives you b cubed minus a cubed over 3. All right? And this means that the integral of a from a to b of x squared dx is equal to the antiderivative of x cubed over 3 from a to b. So take the difference of the antiderivative x cubed over 3 from a to b, which is you put b here, b cubed over 3 minus, and then you put a here, a cubed over 3. So we were able to find the antiderivative of x and x squared, and this gives us the exact value for the integral of these two functions. And because of the linearity, now we can find the integral of any second order polynomial, right? And so one last thing about the polynomials is that I'm going to jump ahead, but I'll come back to this again later, is that in general, we can show that the integral of a polynomial of any arbitrary order m, remember for polynomial, the m is 0, 1, 2, 3, etc., right? From a to b, polynomial has a very nice antiderivative. So x to you increment the power by 1 and divide it by the new power m plus 1. So integral of xm is xm plus 1 divided by m plus 1. And it's obvious if you're familiar with taking the differentiation or taking the derivative of this function is exactly xm. So the antiderivative of xm is xm plus 1 over m plus 1. And the definite integral, or the integral from a to b, is the difference of this antiderivative from a to b. So you put b here, b to the m plus 1 over m plus 1, and then minus, you put a here, a to the m plus 1 over m plus 1. All right? Now we can use two approaches to prove this. The first approach, just the standard definition and calculate the Riemann sum and take the limit. All right? And then the other one is use the approximating function. What do I mean by approximating function? So in approach 1, which is the standard definition, you put the integral of a and b of f of x d of x. You put it equal to limit of this summation when n goes to infinity. In the approach 2, what we do is that in each subinterval xi and xi plus 1, we approximate the function f of x with some other function. All right? And for example, in the rectangle method, we approximate it with a constant function, right? Each rectangle is basically an approximation of the function, assuming that the function is approximated by a constant function. So in general, we can write this summation in a more general way like this. And this is still a series because we're summing over all the subintervals. But in each subinterval, we can define an exact integral based on an approximating function, all right? So if we know the approximating function, or if we choose a proper or easy approximating function, we should be able to calculate this integral exactly. And then again, the general theorem is that whatever you do, this summation should converge to the value of the integral. So these two summations, the limits should give you the same result. All right? So this was an introduction to the concept of integration. In the next lecture and the next few lectures, we are going to look more into the implementing a Java code and how to write a code to actually calculate these summations and find the integration. Thank you for watching, and I'll see you in the next video.